After computing the quality factor of a capacitor and an inductor, now what I am going to do is I am substituting in this equation. When I substitute in this equation, the value of y will be equal to 1 by RT into 1 plus j. In place of C naught RT into omega naught, I am going to replace it as QE. So this will be omega by omega naught into QE minus RT by omega naught into LP is going to be written as QE. So this term will be modified as QE into omega naught divided by omega. If I take the value of QE outside, then YE will be equal to 1 by RT into 1 plus j QE into omega by omega naught minus omega naught by omega. Now, for further simplifying the derivation part of an admittance, what I am going to do is, I am going to take del as a fractional frequency component. Why, or what is the reason why del should be taken at this case? The reason is, I am considering the quality factor of a capacitor as well as the quality factor of an inductor. We all know that from the concept of a tuned circuit, we will be having a frequency response of a tuned circuit where under low frequency of a tuned circuit, it will be behaving as an inductor, and a high frequency of a tuned circuit, it will be behaving as a capacitor. So frequency is being utilized for both the inductor and the capacitor. So what I am trying to do is, since both the cases are being involved in the portion, let me consider one term that is taken as del, where del will be treated as a fractional frequency component. Fractional frequency component in the sense, I am not saying that it belongs to a capacitor or it belongs to an inductor. It will be a frequency that is being common to both the capacitor and an inductor. That's why I am not taking the entire frequency. I am considering only the fractional frequency. If this is the case, and let me take the value of del as equal to omega minus omega naught divided by omega naught. Meaning is, this omega, I have not mentioned it whether it comes under the category of low frequency or high frequency. I have taken it as a common term, that is omega. That is difference with omega naught, that is a center frequency of the circuit, and it is going to be divided with the omega naught. If it is the case, if I am separating it into two terms, then this can be written as omega by omega naught minus 1. If del is equal to omega by omega naught minus 1, then del plus 1 will be equal to omega by omega naught. We are having a term that is omega by omega naught. So in place of omega by omega naught, what I am going to do is, I am going to substitute the term as del plus 1. And the second term is the reciprocal of this term. So it can be written as 1 by del plus 1. So the resultant value of admittance that will be obtained is y is equal to 1 by RT into 1 plus j into QE into del plus 1 minus 1 by del plus 1. So this term I have written it. Now what I am going to do is, I am going to take the LCM part. If we consider this term, so the y is written as, or y is obtained like this: 1 by RT into 1 plus j into QE del plus 1 minus 1 by del plus 1. Let me take LCM. If I take LCM, it will be 1 by RT into 1 plus j into QE. The denominator term is del plus 1, and the numerator term will be, this portion is del plus 1 whole square minus 1. So we all know that a plus b whole square is equal to a square plus b square plus 2ab. So this term can also be written as 1 by RT into 1 plus j into QE del square 2 del plus 1 minus 1, that is divided by del plus 1. So what happens is the resultant value of y obtained is y is equal to 1 by rt 1 plus j into qe del square plus 2 del divided by del plus 1. So this will be the admittance value of the circuit. Now what is the case is I consider del as a fractional frequency component. Let me consider that del is equal to some 1 by 4, just for an assumption. If del is equal to 1 by 4, del square is equal to 1 by 16, which means when compared to del square is somewhat a lower value. Then what can be done is, since del square is far less than 2 del square can be neglected. Similarly, when compared to del, this del value will be very much lesser than 1.